Hello everyone and welcome to our final topic for calculus, Maclaurin series. Now the Maclaurin series is a way of expressing any function as an infinite polynomial. If you take a look at this formula over here, we can see this is an infinite polynomial. Now why would we want to do this? Well, by just writing a few of these terms out, we can get a pretty good approximation of our function just using a few powers of x, which can be quite useful for getting some estimations. Now there are two ways of finding Maclaurin series. Number one is the more general method, which is using this general formula over here, which by the way is in your formula booklet. For any fx, the Maclaurin series of the function is f0 plus f prime 0 over 1 factorial times x plus f prime prime 0 over 2 factorial x squared plus f prime 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 0 over 3 factorial x cubed, and so on and so forth. In case you wanted to write higher derivatives, this is the same thing as saying f prime 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 0. Make sure to put your bracket there though. Now let's try this question. Find the first three terms of the Maclaurin series of fx equals to ln 1 plus e to the power x. So the first term, if you see over here, we need to find out what f0 is. So we have it that fx equals to ln 1 plus e to the power of x, which means that f0 is just ln 1 plus e to the power of 0, which is just equals to ln 2. Now let's find f prime x using the chain rule, which get e to the power of x over 1 plus e to the power of x. And this just means that f prime 0 will be equals to half. If you see, you substitute 0 into here, 0 into here, this becomes 1 over 1 plus 1, which is half. Now you see for the next term, we need to find f prime prime 0. So let's find f prime prime x first. So we're going to be differentiating this using quotient rule. We have v, which is the denominator, and then we need to differentiate the numerator. E to the power x still becomes e to the power x. And then you have minus the numerator u, and we need to differentiate the denominator, which is e to the power x. And this is over v squared, 1 plus e to the power x squared. Now to find f prime prime 0, this is substituting x equals to 0. And all the e to the power x's, e to the power 0 is just 1. So this will be equals to 1/4. Now this is how we solve Maclaurin series questions in paper 1 using this method. But in paper 2, sometimes you're given higher order derivatives that can be really difficult to differentiate. How are we going to use the GDC to help us? Let me teach you a very simple trick in the GDC that can help you find the first two derivatives at a certain point. But keep in mind, this only works for the first two derivatives. It doesn't work for the third derivative and more. Okay, I've done this before in a previous video, but for those of you who have not watched the ultimate GDC tutorial, I'm going to show you how to plot derivatives into the graph. So you want a graph of ln 1 plus e to the power x, right? That's your original function. Now, you can come here, enter in another function. Let's come over here to press this button, and then press d over d over dx, and then f1x. This will give you the graph of the derivative of ln 1 plus e to the power x. Keep in mind though, it only gives you the graph. You don't know what the actual expression of the derivative is. So here you get the graph of the first derivative. Now to find the graph of the second derivative, come over here to this button again and press d2 over d. d2 over dx squared of f1x. And press enter. Keep in mind, you cannot press d over dx of f2x. If you want to say differentiate this f2x over here, this will not work. It will not give you anything. So don't do that. Only use d over dx or d2 over dx squared of the original function. Now we want to find the values when the first and second derivative is equals to 0. So come over here to the menu, and remember graph trace, we'll trace all. And here it tells you the first derivative at x equals to 0, or basically f prime 0, will be equals to 0.5. And over here, this is covered under the thing, but for the second derivative, when x equals to 0, this is basically f prime prime 0, this will be equals to 0.25. So now that we have our values of f0, f prime 0, and f prime prime 0, let's find the Maclaurin series. So the first term is just f0, which is ln 2. And then we're going to have f prime 0 over 1 factorial times x. So this is just this over 1 times x. That's just half x. And for the next term, we're going to take f prime prime 0, or 1/4 over 2 factorial times x squared. And this is just 1 over 8 x squared. And that's your first three terms of the Maclaurin series expansion of ln 1 plus e to the power of x. Now, the second way of finding Maclaurin series is using the standard Maclaurin series. We have 5 Maclaurin series over here in your formula booklet: e to the power x, ln 1 plus x, sine x, cosine x, and arctangent x. For all these formula, we can substitute x for anything. So we can substitute x for x squared, 5x, x squared plus 1. But if you look at our first question, ln 1 plus e to the power x, we can't just simply substitute e to the power x here, because we get e to the power x, e to the power x, e to the power x. And this over here, with e to the power x's, that's not become an infinite polynomial in terms of x anymore. So that is wrong. So usually, that means we only substitute powers of x into this over here. So let's use the standard Maclaurin series to help us solve this question over here. I've written the standard Maclaurin series for e to the power of x. What we first want to do is to find the Maclaurin series of e to the power of negative 3x squared. So remember from earlier, what we are doing is just substituting all these x's with powers of x. So we're substituting negative 3x squared. So we should get 1 minus 3x squared plus 9 over 2x to the power of 4. Now then we can find the Maclaurin series of fx, which is just x to the power of 4 e to the power of negative 3x squared. So what we're doing is multiplying x to the power of 4 to this entire thing over here. So that's just x to the power of 4 minus 3x to the power of 6 plus 9 over 2 x to the power of 8. Now if we look at this question again, if we were to attempt to do this with differentiation, this will be quite difficult to do manually because we have to use product rule quite a few times. Finally, let's see how we're going to use the Maclaurin series to solve a limit. So let's see this question. Use the Maclaurin series to solve the limit as x approaches to 0 of arctangent x over x. So I've written down the Maclaurin series of arctangent x in your formula booklet. Again, this using the standard Maclaurin series. So what I'm going to do is just substitute that into the limit. And now, if you see, if we divide by x, this becomes 1 minus x squared over 3 plus x to the power of 4 over 5 minus dot dot dot. And this dot 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 are all powers of x. We have like minus x to the power of 6 over 7 and then plus x to the power of 8 over 9. And as we use this limit as x approaches 0, this term will become 0, this term becomes 0, and all the powers of x will also become 0. So we can simply see that the limit just becomes 1. And there, we've solved the question. Now here's the summary sheet for Maclaurin series. And that wraps up Maclaurin series and actually the entire IB Math AA syllabus. If you've stuck to the end, congrats on coming so far. I really hope that my videos have helped you to understand and maybe appreciate the math a bit more, even if I may not have gone through the proofs behind all the formula in every video. Hopefully the tips which I've picked up over my 2 years in IBDP will also help you. These are the same tips that help me get not just a 7, but a 95 over 100 overall for IB HL Math AA. So know that you've been in good hands. Once again, thank you so much for watching and hope to see you in the next videos where I'll be covering how to tackle paper 3 as well as covering more IB Math content. Bye!